Hi everyone, I'm Zhitong Chen from the Chinese University of Hong Kong. I'm going to introduce our method P2H for answering distance querying on low networks. See this low network, the shortest path from V10 to V11 is V10, then V15 and V11, which gives the shortest distance 54. There are many algorithms for answering the shortest distance, and the two-hole labeling is the most popular one. The value level of a vertex V is a list of pairs, where each pair contains a vertex W and the distance between V and W on the low network G. To answer a distance query from S to T, we should consider the common vertex, or we call it hop length, in the two query labels LS and LT, and return the minimal length of the path from S then to the hop length V, then to the vertex T. There are multiple methods of two-hole labeling index construction, while for the query algorithm, they follow a similar framework. First, we get the two query labels, and then we get the hop length, and then we look on the hop length to get the minimal distance. Our motivation is to reduce the query time. And the 3D composition two-hole labeling method has the best time complexity, and we find that the remaining thing we can do is how to reduce the hop size. We define a concept average hopping size, which is the average hop size of all possible queries. See this two-hop index. We list all possible queries and its hop size. For example, for query V2 to V3, the hop lengths are V1 and V2, so the hop size is 2. Then we can calculate the average hop size using this equation, and we get a value A over 9, which is the AHS of the two-hop index in this example. As we focus on the 3D composition two-hole labeling, we should introduce the traditional 3D composition first. Given a vertex ordering, we repeat eliminating each vertex. When eliminating a vertex V, we create a tree among V's neighbors, and then we form a tree node MV, and inside MV, we should store a set of vertices SV, including vertex V itself and all V's neighbors. Then we delete all edges connected to V. After the vertex elimination are done, we should determine the descendant and ancestor relationship among tree nodes. In this paper, they do some modifications while doing the 3D composition. They record the weight of the edge by phi-e during the 3D composition. Initially, phi-e is the weight of the edge, but we need to update phi-e when E is created or when the eliminating of a vertex may cause the change of its weight. Then we can use phi-e to generate labels from top to bottom. In this formula, the distance from V to its ancestor A can be calculated by the minimal length of the path from V to each of its neighbors U and then to the ancestor A. For example, see the distance from V7 to its ancestor V15. The set of V7's neighbors is XV7 is equal V7, which is the set of V14 and V15. So we can calculate the distance between V7 and V15 like this. In each tree node, we should have a distance list storing the distance between V and each of its ancestors. Like in the tree node V7, the distance list is the distance from V7 to V15 and then to V14 and then to V7 itself. While the position of each ancestor is tree height. So we can see that the tree node V15 has height 1. Then the distance from V7 to V15 is at position 1. The tree decomposition can be used for the querying because of this property. Given two query vertices S and T, their lowest common ancestor, LCAST, contains a vertex separator for S and T. Here, a vertex separator is a set of vertices from which any path from S to T should pass at least one vertex. See the query V1, V7. The LCA is V14. The vertex separator is XV14 containing V14 and V15. Then we can get the distance by considering the two paths. One is from V1 to V14 and then V7. The other is V1, V15, and V7. We return the one with the smaller length to be the distance between V1 and V7. There are two types of querying. One is that there is no descendant and ancestor relationship between two query vertices. For example, a query V1, V7, LCA V1, V7 is the tree node V14. So the vertex separator is XV14. That is V14 and V15. Note that the height of V15 and V14 is 1 and 2. So in the distance list, position 1 and position 2 are needed. So we can sum up the distance at position 1 and sum up the distance at position 2 and return the one with smaller value to be the distance. The other is that there is descendant and ancestor relationship between the two query vertices. For example, a query V1, V14, LCA V1 and V14 is the tree node V14. That is, V14 is the ancestor of V1. Now the height of V14 is 2. So in the distance list of V1, position 2 is the answer. Our target is to speed up the query, so we need to reduce the average hop size. We propose two strategies on the branching nodes: the vertex separator optimization and the selective vertex separator projection. While the branching node is a tree node with at least 2 children, and we apply these two strategies after the tree decomposition and the label generation in the index construction. For VS optimization, we borrow this lemma from Chen's paper. Given the two query vertices S and T, let NV be a tree node on the path from S to T, but NV is not the lowest common ancestor. Then SV is cool V is a vertex separator for S and T. For example, a query V1 to V9. Then we can see that the tree node V11 is on the path from V9 to V1. So a vertex separator can be SV11 is cool V11, that is V13 and V15. And it has a smaller size than the vertex separator in the lowest common ancestor. So we can replace the vertex separator in the tree node V13 by the set of V13 and V15. But this replacement is only for a branching node with exactly 2 children. So we propose this lemma using JV to replace the vertex separator XV. The idea of VS optimization is that we can use the union of VS from all children except one. Let's say there is a query ST regarding the tree node V as the LCA, and the path from NS to NV goes through NC1, and the path from NT to NV goes through NC2. So XC1 is cool, C1 is a VS, and XC2 is cool, C2 is also a VS. Thus, as at least one of the vertex separator is covered by JV. That means that JV is also a vertex separator for S and T. Next, it's easy to see that JV is a subset of XV by this formula. Then we may have a smaller hop size. Here is the result after we apply the VS optimization on the left-hand side tree. The idea of VS projection is that some vertex in the vertex separator can be pruned. Let V be a branching node and S be a descendant of V. Let C1 and C2 be two vertices in JV. If the shortest path from S to C1 goes through C2, then C1 can be pruned by C2. So we define the projection JVS to be the set of vertices which cannot be pruned. But we should limit the number of branching nodes doing the projection because it's time consuming and space consuming. So we propose the static VS projection. The idea is to set some branching nodes which can reduce the average hop size significantly. The feature of these branching nodes is that they have a high coverage. So our solution is like this. Calculate the coverage of each branching node, and then pit top K branching nodes in terms of the coverage, and then calculate the reduce of AHS for the top K branching nodes, and pit top D branching nodes in terms of the reduced AHS. Here are the algorithms for index construction with two strategies applied. and how these two strategies are used in the query algorithm. We also consider tree extensions. First, we use multiple steps for index construction. As we find that the VH projection takes more than 90% of the construction time, but it can be highly parallel. Next, we consider the index maintenance. For the case that edges update weights, we can use a bottom to top manner to update the file values of edges, and then a top to bottom manner to update the labels. And we extend our master to the directed neural networks by storing the labels and the projections with two directions. Next are the empirical studies. We compare our master P2H with PHL and H2H on A and directed neural networks and 5 directed neural networks catching from the OpenStreetMap. Our measure achieved the smallest average hop size and the shortest query time accordingly on both undirected neural network and directed neural networks. While it takes comparable construction time and storage, the index maintenance also performs well when compared to rebuilding the whole index. In this paper, we propose a new algorithm called P2H for efficient shortest distance querying on neural networks. And we introduce a metric called hop size for the query efficiency, and we show that P2H gives rise to small hop size. We also propose an index maintenance mechanism for edge weight change, and we can handle directed neural networks. Our experiments on real neural networks show that P2H significantly outperforms state-of-the-art methods. Thank you.